Okay, so really non-professional video number one. We're going to talk about acid-base properties of salt solutions because some of you were confused by this. Right now I'm looking at an example that is actually on page 585. So I'm going to work through that example and then just talk a little bit about it. Okay, so you have a 0.10 mole per liter solution of sodium nitrite. Okay, that is not a typo. That is nitrite, not nitrate. If you forget the difference, just as long as you recognize nitrate is the conjugate, or is the anion, oh, that's just me smudging, of the strong acid, nitric acid, right? So some of this stuff is a recognition. So you're looking at the ions that are involved in this ionic compound, and then thinking about what each ion may or may not do with water. So sodium is the cation of a strong base, sodium hydroxide. So sodium will not have any sort of interaction with water, okay, because it is essentially the conjugate acid of a strong base, so it's a very, very weak acid. It's not going to do anything with water. It's not going to hydrolyze water. Then look at this. And some of this, like I said, is recognition or non-recognition. So even if you forget that this is nitrite from grade 11, you recognize that it is not an anion of a strong acid. So remember the strong acids that I expect you to recognize: nitric acid, hydrochloric acid, hydrobromic acid, sulfuric acid, but only the first ionization, phosphoric acid, but only the first ion. So you recognize that this is not part of a strong acid, okay? Therefore, it could be part of a weak acid, right? And then you can think about what it is going to do maybe with water. And sometimes it's helpful to think about water as being protons and hydroxide because it is at equilibrium with itself, forming protons and hydroxide, right? And then think about what this is going to do with either protons or hydroxide. It's not going to hook up with hydroxide. What it could do, though, because it's a negative ion itself, what it could do, though, is it could hook up with protons. So it could take a proton from water to form this guy, okay, which releases hydroxide from the water. So essentially, what you need to recognize is first, this is going to have an interaction with water, and second, that interaction with water will form a basic solution. How basic, you might ask? Well, you actually have information that allows you to calculate the actual pH. So qualitatively, you're going to say it's a basic solution, okay, because of how this guy interacts with water, okay? Then what you need to do is set up your little ice table, okay? I'm actually going to clear, that's not clear, there's an eraser. I told you it was a non-professional video, and I don't know why it's not erasing this stuff underneath, okay? And never mind. You're going to set up a little ice table. Oh, what happened? Okay. Ignore me for a second. Okay, so set up an ice, and why is it blue? Set up an ice table with this equilibrium system, okay? And this is terrible. I'm going to go to another slide, okay? There we are. Okay, so I've got my NO2 interacting with water, taking a proton from the water, releasing hydroxide from the water. This concentration was 0.10 moles per liter. Okay, so that's your initial concentration. Remember, you want to know what the actual pH is, so keep your eye on what it is we're actually trying to solve for, okay? This concentration, 0, okay, because remember, we put in sodium nitrite into solution. So you have some of that at 0.10 moles per liter. You don't have any of this guy, and you don't have any of this guy because we're ignoring autoionization of water. So the equilibrium will be 0.10 minus X X and X, okay? We can use the hundredth rule, be prepared to justify, okay? But if I take the concentration divided by the, in this situation, it will actually be a Kb value of this guy that I'm going to be setting all of this up to. So compare it to the Kb value for NO2 ion. You'll find that you can disregard that X. So I need to look up that Kb value in a second, but I'm going to set that up to x squared over 0.10, okay? Now, if you are just given the Ka value for this, and let's approach it that way, because sometimes in a question you'll be given the Ka value for the weak acid partner of the base that you are looking at. You can kick that over to a Kb value as long as you recognize that Ka times Kb is going to give you Kw. Okay, so I'm just going to pause for a second and look up that Ka value. Okay, so I looked it up. The Ka value for this acid is 7.2 times 10 to the power of -4. Okay, so again, you're kicking that over to a Kb, because that's what this expression is in terms of. And in case you're wondering how you know that, you're looking at hydroxide on the right-hand side. So whenever you have hydroxide on the right-hand side, you're dealing with a Kb expression. So you need a Kb constant, okay? The Kb will be 1.4 times 10 to the power of -11. And just to go back to that 100th rule, 0.1 divided by 1.4 times 10 to the power of -11 is way bigger than 100. So we definitely are safe to disregard that X. All you're doing is you're rearranging and solving, but be aware what you are solving for here is X, but X is the concentration of hydroxide. So you will get a concentration of hydroxide equal to, I'm assuming the textbook is correct because I don't have my calculator handy, 1.2 times 10 to the power of -6. Kick that over to a pH value because that is what you really want. The pH value will be 8.08. Two numbers after the decimal place corresponding to 2 sig digs in your concentration information. Okay, in case you want more, I'm looking at some questions on page 588. And I am looking at question number 3 for no particular reason. What you want is the pH value of, this time, a 0.30 mole per liter solution of ammonium nitrate. So again, recognition is half a battle. I recognize that this anion is the anion of a strong acid, nitric acid, okay? Therefore, this anion is an extremely weak base. Therefore, it's not going to have any sort of interaction with water. Look at your other possibility. This is ammonium. This is the conjugate acid of the weak base ammonia. So this will interact with water. I'm not going to bother showing the water as an acid. Okay, so it will donate a proton to water, forming hydronium. Again, I'm abbreviating here. And be in an equilibrium with its conjugate base partner ammonia. So you have an acidic, that's what that says, acidic solution. How acidic, you might ask? Well, stick everything into an ice table. 0 because we're disregarding water. 0 because we don't have any, okay, because we're starting with ammonium nitrate. At equilibrium, 0.30 minus X. Look how easy this is becoming. X and X. Set this up equal to, it needs to be the Ka of NH4+, which I can get from the Kb of that through Kw. So again, if you're given the Kb in the question, and you need the Ka, by the way, you need to recognize that you need a Ka because you see protons on the right-hand side. You're going to set up that calculated Ka, if it's not given to you directly, to x squared over 0.30 because this Ka, you're assuming, but again, we can prove it, is going to allow you to disregard this X. So I'm going to get the Ka, actually I'm going to get the Kb. Okay, give me a second, I'm going to look it up. Okay, so I've looked up that value. The Kb for ammonia is 1.8 times 10 to the power negative 5. Therefore, kick it over through the Kw. So you're going to take your 1 times 10 to the power negative 14, divide by that Kb value. You will get a Ka of 5.56 times 10 to the power of negative 10. This time, because this is a Ka, once we solve for X, we have proton concentration. So just go ahead and solve for X. I'm just going to report the final answer. So I'm going to take my Ka times your 0.3, square root of that, and then take the negative log of that. I get a pH value of 4.89. But again, check it, make sure that it is also what you get. And that makes sense because it is acidic. And that's what you have going on here. You have a weak acid producing proton in its equilibrium. The other sort of question that you might get could be, I'll do something a little bit different. Ammonium nitrite. Okay, this is comparable to the question in your textbook on page 588, number 5, but a little bit different. So here, again, it's recognition. We've already talked about this. This is a weak acid, okay? So it's going to be a proton donor in solution. So that's going on, and this is telling you that it's going to result in an acidic solution. But then also this situation over here, I'm going to flip to a different color here. We saw this one already, okay? This is the anion of a weak acid, okay? So it is actually going to accept a proton from water to form its, I'm just squeezing it in here, conjugate weak acid and release hydroxide from that solution. So this is telling you it's going to be basic. I'm only going to ask you to do this qualitatively, so we're not going to actually calculate the pH. I just want to know, is it acidic or is it basic? Because they're both kind of telling you, like this is telling you I want to be acidic, this is telling you I want to be basic. You're looking for the dominant system. So what you're going to do is compare the Ka of your ammonium, which you can get through ammonia. I think we already calculated this. I think it was the, again, correct me if I'm wrong, not out loud because I can't hear you.
At this time, we've been instructed to go to a hold and secure.
Great, there's a hold and secure. I'm going to pause for a second. That's okay, nobody's panicking, so we can carry on with this. So that's the Ka of your ammonium. I also now want to compare it to the Kb for your nitrate, which I can get from the Ka of this. Now, I forget exactly what that was from the previous slide, so I'm just going to pause for a second and look it up. Okay, it was 1.4 times 10 to the power negative 11. Now, if it doesn't happen to be that, it's not a big deal. Just get the gist of what's happening here, okay? So the Ka tells you to what extent you have these protons in solution. The Kb of this system tells you to what extent you have hydroxide in solution. And then you compare. In this situation, your Ka is bigger than your Kb. So what that means is this situation that's happening over here is the dominant system. So I would expect that you have an acidic solution, okay? If, now this wasn't the case in this situation, but if you had a Kb that was bigger than your Ka, that's going to tell you that your Kb expression is dominant and you have a basic solution. If you have a Ka that is equal to your Kb, then I'd expect you to have a neutral or pH 7 solution, pH 7 at 25 degrees Celsius. Okay, and this is actually the situation that page 588, number 5 leads you to. Okay, so take a look at page 588, number 5. go through the process, but what you will find is this situation, Ka equal to Kb, and that would be a neutral solution. But if they're not exactly equal to one another, you're looking at who's the dominant system to decide if it's acidic or basic, but only qualitatively. Now the other thing that you could run into is amphoteric ionic compounds. I love my writing, it's fantastic. Okay, best way to do this is with an example. By the way, you're not going to have both ions that are amphoteric, but take a look at this guy.
Can I have your attention, please?
Okay, so back to this. This guy right here, no effect on pH. You need to think about what this can do. Okay, now take a look at this ion. Okay, this is like the midpoint of, so remember we talked about amphoteric species. Carbonic acid can release one proton and form hydrogen carbonate. Sorry, the writing's terrible. Okay, but then this hydrogen carbonate can release another proton to form carbonate. Okay, now hydrogen carbonate, or carbonic acid, sorry, is a weak acid, so both of these will be equilibrium systems. So we talked about this even in the context of polyprotic acids, but this guy right here, because he can donate a proton like this and also receive a proton to go back the other way, he's amphoteric. Okay, so that means when you're considering how this guy could interact with water, you have to consider both possibilities, right? So he could donate a proton to water, forming an acidic solution, okay? And then you would have carbonate. Or he could accept a proton from water, releasing hydroxide from that water, and form carbonic acid. Okay, so now you need to consider which is the dominant system. So it's comparable to what we were just looking at, where you're comparing a Ka and Kb, but you really need to understand what K values you're looking for here. Okay, I shouldn't have erased what I just did. I'm going to clear some space up here right in front of you. La-di-da-di-da. Okay. Okay, so now what you see is the Ka1 and the Ka2 for carbonic acid. You need to think about how these values are going to apply to you deciding which of these two systems is the dominant system to decide if what you're going to have is an acidic or basic solution. Okay, so it's pretty obvious, hopefully, looking at this first system here, you're looking at the second ionization of carbonic acid. So you're looking at the Ka2. Which is, I've looked it up, it's up there, 4.7 times 10 to the power of negative 11. Okay, in terms of this system, you need to think about what's happening here and what you need. This is a Kb. You need a Kb here to compare to this Ka. But you need the Kb of this, which you can get from the Ka of its conjugate-based partner. That's a Ka1. Okay, so you need the Ka for carbonic acid, your H2CO3, which is the Ka1. So you need to get the Kb by taking Kw, divide by the Ka1, and whatever that value is, you're comparing to this Ka2 to decide which is the dominant system. So I'm going to quickly calculate what that Kb value is. The Kb is 2.3 times 10 to the negative 8. Oh, not 18, that's just an 8. Sorry, okay, so times 10 to the negative 8. So then trying to decide who's dominant is going to be a basic solution because you have a situation where your Kb is greater than your Ka for your amphoteric species in equilibrium in solution. Okay?